And here we see Mercury catching up to us on this side of the sun, moving against the background stars. It overtakes us, and now it's going around the backstretch. When it overtakes us, it goes back, and it looks like it's going the opposite direction.
Mercury is the closest planet to the sun, a blistering rock spinning through fire and shadow just 36 million miles away from our star. At first glance, it seems barren, lifeless, burnt and broken. But get closer, and Mercury becomes anything but dull. Because buried beneath the layers of heat-scorched rock and ancient craters are puzzles we still don't understand. Water where there shouldn't be. Ice clinging to regions untouched by sunlight. A magnetic field that by all logic shouldn't exist. And craters, thousands of them, with forms and structures no other world in the solar system displays. Mercury is strange. And the more we study it, the more it seems like a piece of the early solar system, frozen in place, but not asleep. Let's start with the basics. Mercury is small, just over 1,500 miles in radius, a little bigger than the Moon. Yet it's incredibly dense, denser than you'd expect for a world its size. Its orbit is wild. Unlike Earth's near-perfect circle, Mercury's path around the Sun is stretched and eccentric, more like an oval than a ring. Depending on where it is in orbit, it can be as close as 29 million miles or as far as 43 million miles from the Sun. That means not only does the amount of sunlight it receives vary, so does its speed and behavior. Now here's where things get weird. You'd think Mercury would spin rapidly, given its proximity to the Sun's massive gravity. But it doesn't. One Mercurian day, one full rotation on its axis, takes 59 Earth days. But the orbital period? Just 88 Earth days. That means that every 2 Mercury years, the planet rotates exactly 3 times. This strange synchronization, called a 3:2 spin-orbit resonance, is rare. And it didn't just happen by chance. Some scientists believe Mercury once spun differently, locked in a tighter rotation, until something hit it. Something big, that's supported by the craters, some of them enormous, that scar its surface. One of them, the Caloris Basin, stretches nearly 1,000 miles across. The impact that created it may have sent seismic shockwaves around the entire planet. But there's another theory, that Mercury has always been like this, in 3:2 resonance from the beginning. It's one of many unanswered questions. Now, let's talk temperature. Mercury is the planet of extremes. When sunlight hits its surface, temperatures soar to over 800 degrees Fahrenheit, 430 degrees Celsius. But at night, without an atmosphere to hold in the heat, the planet plummets to minus 290 degrees Fahrenheit, minus 180 degrees Celsius. No clouds, no weather, no atmosphere thick enough to create wind or distribute heat. And yet, there's ice. Yes, ice. At Mercury's poles, deep in permanently shadowed craters, radar and imaging have confirmed something impossible: deposits of frozen water. Protected from direct sunlight, these shadowed regions never warm up, allowing ice to survive. But it raises a deeper question. Where did the water come from? Comets? Solar wind? Or is there water locked beneath Mercury's crust, seeping up through fractures?
We still don't know.
That's not the only surprise. Mercury has a magnetic field. It's weak, just 1% the strength of Earth's, but it's real. And it shouldn't be there. To generate a magnetic field, a planet needs a moving, conductive liquid in its core, like Earth's molten iron. But Mercury is small. Small planets should have cooled down and solidified long ago. And yet, Mercury still has a liquid metallic core, and it's active enough to power a magnetosphere. Scientists believe that Mercury's core makes up over 80% of its volume, by far the largest core-to-crust ratio of any rocky planet. It's like a metal ball with a thin shell of rock. That unusual density suggests either Mercury formed in a region rich in metal, or it had much more mass in the past and lost most of its outer layers in a violent collision. Imagine a world the size of Mars, slammed by something massive, stripping away the crust and leaving behind this shrunken, metallic survivor. Whatever the cause, Mercury today is an exposed planetary core, still hot, still magnetic, and still spinning slowly in the furnace of the inner solar system. And that magnetosphere? It's not peaceful. When NASA's Messenger spacecraft flew past Mercury, it observed magnetic tornadoes, twisted flux tubes of solar particles slamming into the planet's surface. That magnetic field isn't a perfect shield. It's patchy, leaky, bursting with electric current where sunlight pours through. In those moments, solar wind from the sun interacts directly with Mercury's surface, kicking up atoms and sending them into space. This process helps sustain Mercury's exosphere, a thin, ghostly envelope of atoms, including sodium, potassium, and helium, that hover around the planet. It's not a true atmosphere. It's constantly being lost to space and replenished by the bombardment of solar wind, micrometeorites, and outgassing from the surface. But it's there, and it's dynamic. Now, let's look at the surface. At first glance, Mercury looks like the moon, covered in craters and ancient plains. But the deeper you go, the stranger it gets. Mercury's crust has features that exist nowhere else in the solar system. Ghost craters, polygonal craters, hollows, scarp ridges, and even radial ejecta rays that stretch thousands of miles. Some craters are ancient, like the 4-billion-year-old basin Rachmaninoff, showing signs of volcanic flooding and chemical weathering. Others are so fresh their ejecta blankets still shine with youthful brightness, like Hokusai crater, which displays rays stretching over 2,800 miles, the longest known on Mercury. These structures aren't just scars, they're time capsules. Because Mercury's lack of weather, erosion, or tectonic drift means these features don't fade. They persist. And by analyzing them, their layers, their depth, their shape, we can reconstruct Mercury's geological history. Some parts of the surface are almost smooth, ancient volcanic plains, where lava once flooded low areas and cooled into vast, featureless basins. Elsewhere, the crust has buckled and fractured, creating wrinkled ridges and lobate scarps, signs that the planet has shrunk over time as its core cooled. Yes, Mercury is literally shrinking. Over billions of years, it has contracted by several miles in radius, squeezing its surface and leaving behind massive fault lines. And then there are the hollows, shallow depressions with flat floors and no raised rims, often surrounded by bright reflective halos. These features are unique to Mercury, found nowhere else. Scientists believe hollows are created by the loss of volatile elements, substances like sulfur and sodium, which evaporate in the extreme heat and leave behind collapsed voids. But the process isn't ancient. Hollows appear young. Some may even still be forming today. That means Mercury's surface, while quiet on the outside, isn't frozen in time. It's changing. Slowly. Relentlessly. And what about Mercury's rings? That's right, Mercury has a dust ring. Not a classic ring like Saturn or Jupiter, but a subtle halo of dust that follows the planet in orbit, stretching across millions of miles. It was discovered accidentally when scientists tried to find a dust-free zone near the Sun. Instead, they found a persistent trail of particles surrounding Mercury's path. It's believed these particles come from micrometeorites constantly impacting the planet, releasing dust that becomes trapped in its orbit. And similar dust trails may exist around other exoplanets, too. So how do we know all this? 2 spacecraft changed everything. The first was Mariner 10, launched in the 1970s. It gave us our first close-up images of Mercury, nearly 3,000 photos, and revealed that the planet was cratered, barren, and strangely magnetic. But Mariner 10 never entered orbit. It flew by Mercury just 3 times, imaging less than half the surface before shutting down. It was a glimpse, a whisper from a world still hidden. Then came Messenger. Launched by NASA in 2004, Messenger, short for Mercury surface, space environment, geochemistry, and ranging, didn't just fly by Mercury. It went into orbit, circling the planet more than 4,000 times between 2011 and 2015. Over its mission, Messenger sent back over 250,000 images, mapped the entire planet, and made a series of discoveries that scientists are still analyzing today. Messenger confirmed that Mercury's crust is rich in sulfur, a clue that the planet's volcanic history was more intense than expected. In fact, volcanic plains cover much of Mercury. The spacecraft found evidence of ancient lava flows, smooth volcanic basins, and pyroclastic deposits, the remains of explosive eruptions. This suggests that in its youth, Mercury may have been a molten world, with oceans of magma pouring across its surface. Those flows didn't just reshape the terrain. They may have buried older craters, explaining why certain crater sizes are strangely missing from Mercury's record. Some sizes are underrepresented, as if they were erased by later volcanic resurfacing. Messenger also measured elemental abundances, showing that Mercury's crust is unlike Earth's, more reduced, chemically speaking. It has a composition rich in magnesium and calcium, but poor in iron at the surface, despite the huge iron core below. This points to a planet that formed very close to the Sun, in a hot zone of the protoplanetary disk, where lighter silicates were rare and metal-rich materials dominated. It also supports the theory that Mercury may have lost mass, either from collisions or from being stripped by early solar radiation. But one of Messenger's most surprising discoveries was at the poles. Using neutron spectrometry, the spacecraft detected hydrogen signatures, which, combined with reflectivity data, strongly suggest the presence of water ice in permanently shadowed craters. Despite Mercury's searing heat, these deep craters, never exposed to sunlight, act like cold traps, preserving water delivered by ancient comets or possibly released from Mercury itself. Some scientists believe there may even be liquid water under the surface in these regions, though that remains unconfirmed. The idea that water, and perhaps volatiles like carbon or nitrogen, could survive on Mercury has major implications for understanding the early solar system, especially how water was distributed across rocky planets. And then, Messenger ran out of fuel. In April 2015, it crashed into Mercury's surface at over 8,700 miles per hour, carving a new crater and becoming part of the very world it studied. But the mission left behind a legacy, a complete global map, a refined gravity model, chemical data, and questions, lots of them. Why is Mercury's magnetic field offset? Why are hollows still forming? What keeps its core partially liquid? What really happened in its early years? Those are the mysteries Bepi Colombo is now racing to solve. Launched in 2018 by the European Space Agency and Japan's Space Agency, JAXA, Bepi Colombo is a dual spacecraft mission that's expected to arrive in Mercury's orbit in 2025. Its job? Pick up where Messenger left off, but with even more advanced instruments, more sensitive detectors, and a new approach. While Messenger orbited close and alone, Bepi Colombo carries two orbiters, one for mapping the surface and studying the interior, and another for monitoring the magnetosphere. Together, they'll answer critical questions about why Mercury's magnetic field is lopsided, how its core and mantle formed, what mechanisms cause hollows and surface collapse, how the planet's orbit, temperature, and chemical composition evolved. But Bepi Colombo's most ambitious goal is to reconstruct Mercury's origin, and by extension, understand why the inner solar system has 4 rocky planets so different from one another. Because here's the bigger truth. Mercury doesn't fit. It's too metal-rich. It's too dense. It has a core too big for its size. It has a magnetic field that makes no sense, and water ice that shouldn't exist. It's like a leftover core of a much larger world, or the survivor of a cosmic catastrophe we haven't fully grasped. Some theories suggest Mercury is the stripped core of a protoplanet that collided with another body, a remnant of a chaotic, violent past where worlds crashed, merged, and shattered in the early days of the solar system. Others propose that Mercury's orbit was reshaped by migration. As Venus and Earth moved outward, Mercury was trapped in a chaotic dance, its crust shattered, its shape changed forever. Still others say Mercury's position, deep in the gravity well of the Sun, may be the reason why it evolved so differently. The truth is, we don't know, but that's what makes Mercury so important. It's not just the innermost planet. It's a fossil, a relic of early planetary formation, frozen in place, battered but enduring. And it may hold answers about how planets like ours came to be, or what happens when they don't make it. As we wait for Bepi Colombo's arrival, one thing is clear. Mercury isn't just a ball of rock orbiting too close to the Sun. It's a world of extremes, of contradictions, of secrets waiting to be uncovered. And as telescopes on Earth and spacecraft in orbit keep peering closer, one truth becomes more obvious with every new discovery. The smallest planet may be hiding the biggest clues about the origins of everything. If this changed how you see Mercury, hit that like button. If you want to go deeper into missions like Bepi Colombo, drop a comment and let us know. And if you're fascinated by forgotten worlds hiding in plain sight, subscribe, because we're only getting started. From impact basins to polar ice, Mercury isn't done speaking, and neither are we.